Okay, energy. What is the unit of energy? Joule. Work and energy have the same unit. Correct? Because only if you have energy, you can do work. The definition for work is what? Sorry, the definition for energy is capacity to do work. Okay, so they both have the same units. There are other units of energy also, like Joule is the SI unit. The CJS unit is what? Erg. And then you have specific units for energy, not for work, but for energy we use calories, electron volt, watt hour, kilowatt hour. These are all other units for energy. You all remember? Yes. Now we're going to see different forms of energy. One form of energy called mechanical energy. There are different forms of energy like light energy, sound energy. Tell me some forms of energy you've learned in smaller classes. Solar energy. Okay.
Kinetic.
Kinetic and potential energy, two forms of energy. They come under a topic called mechanical energy. That's what we're studying in this chapter. Okay, we're studying about mechanical energy, which is divided into kinetic and potential. What other forms of energy have you learned? Anything else coming to the mind? You said heat, heat energy. Heat is different. Light.
Gravitational potential energy.
Okay, potential energy is divided as gravitational and elastic. Okay, so yeah. So out of all these energies, mechanical energy is one of the energy, and mechanical is divided into what? Potential and kinetic. Okay, and potential is again divided into elastic potential, gravitational potential, and so on. Okay, now let us see what is this mechanical energy first of all. So what's the definition of mechanical energy? It's not here.
When it is not in motion.
Here. The energy possessed by a body due to its state of rest or motion. Now, if it is at rest, then it has potential energy, and if it is at motion, it has kinetic energy. For example, if I'm holding this ball up over here, what energy does the ball have? If I'm holding it, potential energy, gravitational potential energy means gravity wants to pull it down, but I'm holding it, so it's not going down, but it has an energy, it wants to come down. Now, when I release it, what happens? That potential energy got converted into kinetic energy. Okay, it's always conversion. Potential, all energy, any form of energy is always getting converted, right? From one form to another form. Okay, there is no, you cannot think of any example where energy is created. It's always converted from one form to the other form. So now, the higher I lift this ball, the more potential energy it will gather. And when I leave it, that gets converted to more kinetic energy. So if I leave this ball from the top of this building, it will come at very high speeds, right? Because on the top of the building, it had very high potential energy. And when I left it, that whole potential energy got converted into very high amount of kinetic energy. That's why it comes down at a high speed. All right. So what's the definition for potential energy? You can just say the first part. That is the energy possessed by a body due to its state of rest. And what is kinetic energy? The energy possessed by a body due to its state of motion. Got it? If you say rest, then it is potential energy. If you say motion, it is kinetic energy. Okay, so potential energy is represented by the alphabet U, not P. P is used somewhere else.
Power. The potential difference.
Potential difference is V. Power is P. I think momentum is also the small p or something. Momentum. Okay, so there are too many p's already. Capital P is taken, small p is taken. So potential energy is U. Okay. Now examples of objects having potential energy. One is an object at a certain height. One is an example of a stretched rubber band. That you take a paper, put it at the end of the rubber band and pull it back. It has potential energy. But both these are two different types of potential energy. The ball that wants to fall down has what type of potential energy? Gravitational potential energy. And this paper that I'm pulling back,
Elastic potential.
elastic potential energy. Okay. So two types of potential energy. Oh yeah, both are here. Gravitational and elastic. What about a ball that's compressed? A full football, you kick it. When you kick it, it gets deformed. Its shape changes and it wants to go back to its original form. So what type of potential energy does that ball have when it is kicked? Elastic, because it wants to go back to its original form. How can you increase gravitational potential energy?
By increasing the height. Or the-
See, both are not talking. Come here, Beryl. From past 5 minutes, I'm saying something, you're continuously talking. Why do you want to waste everybody's time? Sit in between them. Come this way. Okay, to answer this question. How do we, Leah, tell me, how do we increase gravitational potential energy? Come this way. How do we increase gravitational potential energy?
By frequency.
Increasing the height. Right, the higher you go up, the more gravitational potential energy you have. How do you increase elastic potential energy? Stretching it more and more. Right, a rubber band. Or if it's a ball, then you compress it more to increase. Yeah.
Can you explain elastic potential energy? I didn't understand that.
Means if a body is deformed from its original structure, then it has elastic potential energy. For example, if I take a scale, okay, and I bend the scale, right now the scale has elastic potential energy. It wants to go back to its original form. Okay. If I take a rubber band and I stretch the rubber band, it has elastic potential energy. It wants to go back to its original form. Okay. That is what it is. So deformed state. Here, the definition, the potential energy possessed by a body in the deformed state due to change in its size and shape is called elastic potential energy. Okay. Now, we are only studying about gravitational potential energy, not elastic potential energy. The formula for gravitational potential energy is mgh. Remember, we have seen this formula previously. When have we seen that formula, or what formula was this? Huh? mgh. Huh? Work done against gravity. And here this is potential difference due to gravitational potential energy is also mgh. So why do they have the same formula? First of all, work done, and this is energy. Work done and energy is the same thing. And both of these are against gravity. So work done against gravity or energy against gravity. They're the same thing, right? So yeah, if you take an object higher, the higher you do, like let me see, I'll show you the relationship between work done and energy. If you lift an object higher, say Ahmed is lifting something higher and higher and higher. Now you're doing work by lifting an object higher and higher. Who's doing the work? Ahmed. Now the work that he's doing is getting converted into gravitational potential energy in this ball. Remember, energy cannot be created or destroyed. So if energy is gathering up in this ball, how is the energy gathering up? Where is that energy coming? From Ahmed. His work that he's doing is getting converted into energy, gravitational potential energy in the ball. Okay. So if he does mgh amount of work, that ball has mgh amount of energy in it. Is that clear, everyone? Okay, so that's why both of them have the same formula.
Suddenly freeze. I suddenly freeze because I realized that's Ernie's fault. I have to put it in.
Take. I mean, class.
She's the head of the road.
Okay, now we have already spoken about how we got this formula mgh. Mg is actually from where? Mg is force. Force is mass into acceleration, right? The force is m into g. And this h is what actually? Displacement, s. That f into s formula was modified into mgh. What is the unit for f?
force.
What's the unit of force? Newton. What's the unit of S? Meters. Right. What's the unit of mass? M? Kg or kgf. G?
Meter per second.
Meter per second square. It's acceleration. No, G is acceleration due to gravity. The unit for acceleration is meter per second square. And H, what's the unit of H?
Meters.
Meters. It's height. Okay. So this whole part is talking about how gravitational potential energy increases. It's very simple. You either increase M or G or H. To increase gravitational potential energy, you have to either increase M or G or H because they're all directly proportional to U. Right. So that means, for example, this phone and this pen, which has more potential energy? The phone. Why? More mass. They're at the same height. But since the phone has more mass, it has more potential energy. Which means if I leave it, it will have more kinetic energy. Which means it has more power to damage whatever it falls on. Right? That energy is being converted, no? What if I'm holding two of the same pens? Then they both will have the same potential energy. But say one is higher, one is lower. Which one has more potential energy? The higher. So that again we are seeing that it depends on the height. The higher you take it, the more potential energy. Yeah. So very simple thing. You can just read through that part. As the object is falling down, what is happening to its potential energy? Say it was at a certain height, say 10 meters, and I dropped it till 7 meters height. So what happened to its potential energy? It decreased because at 10-meter height, it had that much potential energy. At 7 meters of height, it has only that much amount of potential energy. Right. So there was a decrease in the potential energy as the body is coming down. So what was happening to the potential energy as the body was falling down? How can energy just simply decrease? It can't just decrease. You can't destroy energy. Yes, as it was falling down, the potential energy was getting converted into kinetic energy, and that's why the object was going at a faster speed. As it is falling lower and lower, what's happening to its speed? It's increasing, right? More it travels, the faster it gets. Okay. So now let's come to kinetic energy. Kinetic energy is represented with the alphabet K. The formula for kinetic energy is, anyone remembers? It's half mv square. You've seen this, right? Half mv square. Okay, so these are the two formulas we have seen. U is mgh and kinetic energy is half mv square. Okay. Now what is this m? M is mass. What is v? Velocity. Okay. So what this formula tells you is that mass and velocity are related to kinetic energy. How are they related? Velocity is speed. My question is, are they directly proportional or inversely proportional? They both are directly proportional to kinetic energy. Because they're in the numerator, no? If any value is in the denominator, then that is inversely proportional. Yes or no? You've seen this hundreds of times, right? Okay, so mass and velocity are directly proportional to kinetic energy. Okay, think of this. I'm giving an example now. Two objects, a train and a car, they're moving at the same velocity. Which one has more kinetic energy? Train. Why? It has more mass. Right, more the mass, more the kinetic energy. Next, let's look at velocity. Two cars are traveling. One is traveling very fast, one is traveling slowly. Which one has more kinetic energy? The fast one, because it has a higher velocity, speed. Okay. Now, whichever formula we take, what's the unit of U? What's the unit of potential energy? Hmm? It's joule, because it's energy. Any form of energy, the unit is joule. Okay. Now what's the unit of kinetic energy? Joule, because it's energy again. Okay. So both have the same unit, that is joule. Standard unit is joule. And then write down these two formulas for potential and kinetic energy.
Anna, another example of potential and kinetic energy is dams also, make the water falls into convert into kinetic energy.
The water in a tank has potential energy, but when you open the tap, then the flowing water has kinetic energy.
Not dam, I mean the dams, like the big dams.
Dam, same thing. Yeah, I was going to say that also. Yeah. So the water in a dam has what energy?
Potential.
Potential energy. And if the dam breaks, then all that potential energy will get converted into kinetic energy. Hydroelectricity makes use of this energy in water. Right? It uses the kinetic energy of that flowing water to turn the turbines so that you can get electricity. Yes?
You
Okay.
explained this in 8th standard.
Yes.
Right?
You are in 8th. Okay. I hope all of you remember whatever you studied. You remember all this, Aman? Aman was not studying that time. Okay. Now we're going to see a relationship between kinetic energy and momentum. This is a very important derivation. The derivation between the relationship, derivation of the relationship between kinetic energy and momentum. Now, kinetic energy formula we know, half mv squared. What is momentum? Momentum is represented with the alphabet P. Remember, I told you P is already taken. Capital P is taken for what? Capital P is used by which unit? Which quantity? Power. So this is small p. Okay, this is not capital P. This is small p for momentum. Okay. Now momentum's formula is mv. Kinetic energy also is using m and v. Momentum also has m and v, which means they're very similar to each other. Okay. If I say an object has high kinetic energy, it means it has a high momentum. It means a body is moving with a high mass and a high velocity. A train has a very high amount of momentum because it has a heavy mass and it's moving at a certain velocity, right? Okay, so they're very similar to each other, but they're not exactly the same. There is a difference. The formulas are different, right? This is half, and there's a v square. For momentum, is there's no half, there's no square. There's just m into v. Okay. So now we're going to derive a formula between k and p, between k and p. In k's formula, there is no p, and in the p's formula, there is no k. But we're going to make a formula where in k's formula you will have p, and in p's formula you will have k. Got it? Okay, so how do we do this? So first we make v the subject. Okay, write down the heading you have to write down. Relationship between, write down, between k and small p. Okay, so k's formula we have, p's formula we have. Leah, what is k's formula? Half mv square. What is p's formula, Beryl? mv. Now from p's formula, let's make v the subject. So what will v be? Take the m on the other side, right? You want to make v the subject. P upon m. Okay, now substitute this v, we'll call this k as 1, and we'll call this as 2. So we'll substitute the value v in equation 1. So now what will kinetic energy become if you put V over here? Half m, and in place of V we are going to put what? P upon m. So it'll be square because V square. How many understood? Okay. So simplifying this, K is equal to what? Half m into P square upon m square. So now m and m will cut. Here one m, and from here one m. Out of the m square we cut one of the m. So we get K is equal to what? 1 upon 2 P square upon m. Or in other words, P square upon 2m. Okay, so this is the formula for kinetic energy if you have P inside of it. Like kinetic energy formula with momentum in it. Now, if you want the other way, if you want P to be the subject, how do you make P the subject here? You take the 2m on this side. So that'll be what? 2mk is equal to P square. Yeah, square root both the sides. So you'll have P is equal to square root of 2mk. This is the formula where P is the subject. Write down this much. This is the derivation of the relationship between K and P. Okay, we'll move on. Done, everyone? Now there's one more theorem, but no two theorems in one day. Learn one theorem at a time. Learn this theorem. When you go home, you should be able to write down this theorem within a minute. Write it in such a way that you're able to solve it within a minute. Okay, it comes in exam quite often. Okay, the next theorem, which is work energy theorem, we'll do on another day. Now we'll see forms of kinetic energy. We saw forms of potential energy. What were the forms of potential energy? What are the forms of potential energy? Gravitational and elastic. Now we're going to see forms of kinetic energy. So there are three forms of kinetic energy: translational, rotational, vibrational. Translation means the object is moving in a straight line. First chapter also you had straight force and rotational force, right? Yeah, but that was force. This is kinetic energy. Yeah, so same thing, but yeah, this is about kinetic energy. So translational kinetic energy is possessed by a body if it's traveling in a straight line. Rotational kinetic energy is if the body is rotating. For example, the fan is rotating. The earth is moving around the sun. The door is revolving around an axis. So they all have rotational kinetic energy. Third one is vibrational. That means the object is just moving front and back, moving back and forth. Okay. Example of rotation, vibrational is what? A string, a guitar string. Okay. This scale, if I clamp it at one end and then I hit this, it vibrates. That is vibrational kinetic energy. So what it means is whatever, I mean, all these three forms are forms of energy, whether the body is moving in a straight line or moving around or just vibrating, it still has kinetic energy. Okay, here you have the differences between potential and kinetic energy. Just read through them, learn them. The main difference is in potential energy, the object is not moving. In kinetic energy, the body is moving. Okay, and both can interchange. Like potential energy can change into kinetic, and kinetic also can change into potential. Both ways, right? See, what if I throw a ball up? I throw a ball up. So tell me all the conversions. First,
bring against gravity.
before that, my energy. I'm using my energy, right? So my energy is getting converted into energy in the ball. Okay, now energy in the ball. As the ball goes higher, what energy is it gaining or losing? So as soon as I throw the ball has so much amount of kinetic energy. It's going at a very high speed. And as it's going higher and higher, what energy it is also gaining? Potential energy. So as I throw it, it has kinetic, and as it goes higher, it gains potential. Okay. Now as the ball is going up, finally it goes to a certain point and then it starts coming down. So now it has reached maximum potential energy. And as the ball is coming down, that potential energy is changing into kinetic energy. It already has kinetic energy, and now there's more kinetic energy coming down. Okay, so it's all just a lot of energy changes taking place. Potential to kinetic, kinetic to potential. Even a pendulum. If you're swinging a pendulum, you have that later on. We will be seeing that time. But there also you can see potential to kinetic to potential to kinetic. It's continuously changing. Second one is potential energy is equal to the work done in bringing the body to its change state. Potential energy formula was mgh. Even the work done to bring it up to that height is also mgh. So that's what they're saying over here. It is equal to the work done. Kinetic energy is what? It is equal to the work done that can stop the moving body before it comes to rest. Now, for example, there is a car coming towards me. It has a certain amount of kinetic energy. Say it has 10,000 joules of kinetic energy. So here what they're saying is, if I want to stop the car, I have to go in front of the car and apply how much amount of energy? 10,000 joules. Because the car had 10,000 joules of energy coming towards me. And if I had to stop it, then I have to apply a force of, not force, I have to use energy of mine. How much energy of mine I have to use? 10,000 joules of my energy I have to use to stop that car. Right? That's what the second point is. See, I'll read it again. It is equal to the work done or work that a moving body can do before coming to rest. Okay, this also you'll understand it more when we learn about the work energy theorem. See, work energy. I have to do work. No, who's doing work? Car has kinetic energy, and I have to do some work to stop that car. So they're related to each other. If the car has more energy, then I have to do more work to stop it. If the car has less energy, then I have to do less work to stop it. Okay, so this is talking about that. Third point, potential energy, it can change only in the form of kinetic energy. Potential can change into kinetic. Potential can only change into kinetic. Water in the dam has what energy? Potential. That potential cannot change into any other form of energy. Potential can only change into kinetic. But kinetic can change into any other form. For example, that moving water has kinetic energy. When it falls on the turbines, what energy does it gain? Like it's that kinetic energy. It's rotating, and that rotational kinetic energy is changing into electrical energy. Right. So kinetic energy can change into any other form of energy, like electrical. Or for example, if a car is moving and it puts brakes, it skids. So that skidding forms what type of energy? When the tires skid on the road, it forms heat energy because friction, right? So kinetic energy can change into heat energy. So like that, kinetic can change into many forms. The fourth difference, potential energy, it does not depend on the speed of the body because it's at rest. And kinetic energy depends on the speed. Speed means velocity, right? The formula is what? Half mv square. So you can see it depends on speed. Now here there are so many examples of conversion of conversion of potential to kinetic. If there's a nail over here, I want to hammer the nail down. What do? Take the hammer. I don't have to use so much force. I just have to leave the hammer down, right? So the higher I take the hammer, the more kinetic energy is produced and the nail can be struck easily. Another example is of a spring. These toys are there, you have to wind it and then leave it, it'll go front. Or you pull it back and you leave it, it'll go front, right? So inside that, there's a spring. Now, when you pull that toy behind, that spring is rotating and creating potential energy inside of it. And when you leave it, what happens? All that potential changes into kinetic energy. Okay. Or a bow and arrow. You pull the arrow behind using the bow. What energy does the arrow have? Potential energy. And when I leave the arrow, it turns into kinetic energy. Another example is of a compressed spring. So right now, if I put a ball on the compressed spring, what energy is there in this ball and the spring? Huh? if I'm holding it down. I'm not letting it go. I'm holding it down. It has potential, elastic potential energy. And when I leave it, the ball flies away, right? So now the ball has kinetic energy. So very simple examples of conversions of potential into kinetic energy. Okay. All right. Before you close, we're done with this, but next is again very easy, different forms of energy. I want you to read this by yourself. Okay, it's what you have studied in some smaller classes, like what is light energy, what is hydro energy, what is heat energy, all these things. Okay, so that is the rest of the chapter, and the last part is this conversion from this form to that form. So it's all theory now. The B part is very simple. It is very basic things. It is one of the easiest topic in physics. The next two topics. Right. So tomorrow, what should we do? We'll continue with physics. Try to finish this off, and we'll not do maths tomorrow because you have your test. Yeah, if there's any doubt, we'll clear that in maths. So carry maths, carry physics, and probably we should do another subject, biology. By the way, you're taking biology. Okay, so stay back. So get biology tomorrow. Maths, physics, and biology tomorrow. Computer will do. It's too smart for me. Okay, I'll see you all tomorrow then.
The test is on Thursday, right?
Test is on Thursday. 3 chapters in maths: reflection, linear, what? Linear inequations, right? Yeah, and quadratic. All right, bye everyone. See you tomorrow.
Bye, man.
Bye. Okay, so nuclear fusion is where two atoms join to form one bigger atom. And nuclear fission is what? Yeah, one atom splitting into two smaller atoms. Okay, nuclear fission. Now, these two forms of energy, nuclear fission and nuclear fusion, they produce the highest amount of energy that you get. That's possible actually. Okay, so it can be used in a good way also. It can be used in a bad way also. How can we use nuclear energy in a good way? Electricity. That's the only thing we need right now on Earth. Producing electricity. That is good. Bad is what? A bomb. Right? You can create a nuclear bomb which can be very, very dangerous. Okay, which were the two most famous nuclear bombs, atom bombs? Hiroshima and Nagasaki. Okay, so that was a nuclear bomb. It was a nuclear fission. Okay, nuclear. Both these reactions. To start the reaction, you need a very high amount of heat energy. Okay, so nuclear fission is possible on Earth. There are ways to perform nuclear fission reactions. When you cause two atoms to bombard, or one atom to bombard with a nucleus or a neutron of another atom. When they hit each other at such very high speed, almost the speed of light, they make it go as fast as light. And then when they bombard it, that atom will split into two. Okay. Now when it splits, it produces this very high amount of energy, heat energy. It explodes. Nuclear fusion needs more energy to start the reaction than nuclear fission. You need much more amount of heat energy. So this reaction is very difficult on Earth to be able to get that high amount of heat energy. Okay, that's why it only happens in the sun because the sun is very hot. So nuclear fusion takes place in the sun. Now Einstein, you know Albert Einstein, right? Albert Einstein came up with one formula, a relationship between mass and energy. Did you ever think that mass and energy are related? Mass means the weight of something. How is that related to energy? Okay, but yeah, he came up with a formula. What is that formula? One of the most famous formulas of our century. That is E is equal to mc square. Okay, so here what does E stand for? Energy. What is M? Mass. And what is C? C is speed of light. Okay, so what did Albert Einstein like if you understand this formula, you can understand that the speed of light is a very high value, 3 into 10 raised to 8 meter per second, right? And if you square that, it's much more bigger, right? And you multiply that with mass and you're getting energy. So you can understand that a small amount of mass can produce a very high amount of energy. Just imagine mass, say 1 kg. You multiply that with 3 into 10 raised to 8, and again you do whole square for that. So the answer that you get is very big, right? That is the energy that can be produced. Okay. When an object is able to travel at the speed of light, it's something to do with that. When an object travels at a speed of light, you're able to produce a huge amount of energy. Okay. So nuclear energy is based on this. That's why we can see that nuclear energy is very high because of this formula. Okay. All right. The next one is geothermal energy. We spoke about that. That is the energy contained within the Earth's surface. And only in some places in the Earth we can use this geothermal energy. In places where where there are volcanoes. Volcanoes means the internal temperature of the Earth comes to the surface. It comes to the surface only, it comes out as volcano, right? So if that internal heat energy comes to close to the surface, you can use that geothermal energy. Just you need one pipe going in the earth and that pipe coming out of the earth. Push water through that pipe, and what comes out is steam. And then they can use that pressure. It's very high pressure because that water has turned into steam. And high pressure can be used to turn the turbines. Then wind energy is the windmill, right? Very useful, but in places where there is heavy wind, only there you can use windmills. We can't put windmill here now. There's no wind over here, right? You need an open area where it is open and clear. There you can install windmills. One of the cleanest energies, windmills. Then sound energy. Yes, right now we are hearing sound. It is because of sound energy. Sound is produced when a body vibrates. And when the body vibrates, resonance is created, and your ears also start to vibrate, the eardrum, and that passes on through the bones. What are those bones called in the ear? Huh? You have a chapter in 10th where you will be learning about the internal structure of the ear. Okay, those bones are called ear ossicles. Okay, those bones will also vibrate along with that eardrum, and that transfers the sound into your internal ear, your inner ear. All right, magnetic energy. Okay, do we use magnetic energy or it's not used very often? No? Where? Can you think of an example where we use magnetic energy? Okay, bells use magnets. Okay, electromagnet. When you pass electricity, that bell will turn on, right? And that attracts one metal onto the bell. Okay, any other place other than bell, or that's it? Anything that rotates, like a fan. See, a fan has magnets inside of it. The magnets in the fan is causing, when there are two magnets brought close to each other, what happens? When you bring two magnets close to each other, what happens? It either attracts or it repels, right? So there is a force created. So they have made the fan motor. There's a motor in the fan made in such a way that continuously there is attraction repulsion, and that causes the fan to rotate. So every motor is made up of a magnet. Now tell me, where do we use motor? Cars. Okay, not actually. Our cars use something called engines. Engines don't have a motor, but it's different mechanism. But you can think of electric cars. They have a motor, and that motor rotates the wheel. So yeah, anything that moves, anything that rotates has motors in them. And motors are what? Motors are made up of magnets. That's why you see how important magnets are. You were saying not very important, but you see, every vehicle, okay, there is a magnetic uh, part inside of it which causes it to move. Okay, and the last one is mechanical energy, which we already studied a lot about. Two forms of mechanical energy are potential and kinetic. The potential is divided into elastic and gravitational, right? Yeah, so potential and kinetic together is called mechanical energy. Okay, now the most interesting part of this book, I can say, is the conversion. Mechanical to, there are so many conversions here. Now I will tell you, and you tell me an example of where you can see such conversion taking place. Okay, where do you find mechanical energy to electrical energy? Mechanical to electrical. This is electrical to mechanical. Fan is electricity is getting converted to mechanical. Opposite. The generators. Right. Turbine is connected to the generator. So mechanical to electrical is seen inside a generator. You need some form of mechanical energy like water or wind that rotates those turbines, which rotates the generator. And the generator produces electricity. Yes, windmill also. The wind gives you that mechanical energy, kinetic energy, which rotates the turbines to cause electrical energy. Another word for generator, you know what's another word for generator? Dynamo. You heard of dynamo?
Yes.
When I was your age and we had cycles, and if you wanted light in the cycles, night to ride in the night, yeah, when you pedal, the dynamo rotates. Okay, and the rotation of the dynamo it turns on the light, and that's how we could see in the night. Nowadays, we don't need all those. We have LED lights. LED lights are so much more powerful, and they consume so much less electricity. You can put battery, rechargeable batteries, put LED lights, and you can ride your cycle. But in those days, there was no LED. LED is a new technology. You know that, right? When you were small, there were no LEDs. LEDs like what, 10 years old or not even 10 years old. Okay. So LEDs have changed everything. No LED TVs. We are using LED TVs right now. 10 years back, there were no LED TV. Okay. You see where technology has come so far. Okay. That means there were no laptops. That means, okay, say 15 years ago. Okay. They didn't use LED. They used something called LCD, and LCD also is using LED. So before LEDs, like you can't have like these thin screens. You need a big box. That's why TVs also wear a big box and no LED lights. Okay. So LED has changed lighting. Okay. You can just imagine everywhere, the TVs and lights and everything. So yeah, how we used to get lights before when we were small? When we have one small cylindrical thing that is attached to the tire, near the tire. So you have to move it, it touches the tire. And when the tire rotates, that turbine or dynamo, it rotates, and there's a wire that is connected to the light, and the light used to turn on. Okay. All right. So that is mechanical to electrical. Yeah. Now the opposite, electrical to mechanical. What is this? Electrical that is moving something. Give me an example. Fan or an electric car. Right. Wherever there's a motor, any motor is an example of electrical energy to mechanical energy. Mixie, grinder, washing machine. Right. All of these have motors. Yeah, it is ready. Okay, third one is electrical to heat energy. Again, think of your home where you convert electrical to heat energy.
Pressing,
Brushing?
pressing boots.
Oh, pressing the clothes. Yes, iron box, right? Electrical energy is getting converted to heat energy. Any other example? Straightening, hair dryer. All of this is heat. No, heat is being formed. Oven, uh, the oven where you cook, bake. Okay, that is all examples of this. So how? Yeah, iron box. How is this conversion taking place? How is electricity changing into heat? What do they have to do inside the iron box so that electricity changes into heat? See, this is the iron box. Okay. And then you have electricity. There is a live wire and there is a neutral. Very nice photo. See, this is an iron box. Okay. So you have two wires entering into the iron box, a live wire and a neutral. Okay. What goes in through the live is the electricity. And once the electricity goes in the iron box, it has to go out through the neutral. That is how electricity works, right? Now, once this live wire enters into the iron box, In the iron box, you have something called heating rods. There are rods, or there is a coil, a wire that goes inside through, and this wire has very high resistance. Okay, we'll be learning about all this when we go to the chapter electricity. But there's something called resistance. Resistance is not a new topic for you. What is resistance? Obstruction to the flow of electricity. And when there's an obstruction to the flow, what year? Oh, 9th standard, you learned all these things. You should tell it like this. So whenever there's an obstruction to the flow of electricity, what happens? See, electrons are trying to move, but there's an obstruction, so it's struggling to move. So there is resistance. Whenever there's resistance, it produces what? It has to go back through neutral, but it struggles to reach the neutral. So it pushes its way through all the resistance and it goes to the neutral. But in that process of trying to move through, it creates friction. There's so much friction, and that causes heat. Okay, so whenever there is resistance to the flow of electricity, it produces heat. That is how iron box gets hot. They just put a very high resistance wire inside. Okay. Go. Don't come on. Okay. Hey, clear everyone? Next is heat energy to electrical energy. Heat to electrical, opposite. Where do we see this? Solar is not heat, that is light. What? Solar panel is not producing electricity, it is just heating the water. Solar cells is converting light to electricity, right? And solar panel is converting heat to heat only. There's no conversion actually. Huh? Cold means absence of heat. So cold we can't say is a form of energy. The solar panel is just transferring the heat from the sun to the water. It's just transfer of heat. And solar cells, what they do? Solar cells, light energy to electrical energy. Okay, so both are not the answer. Where do we see heat energy to electrical energy? So this is something that you might not know of. Okay, there's a device called a thermocouple. Thermocouple, listen carefully. Thermocouple is two metals, say iron and say copper. Iron and copper. Okay. Now, one terminal, like at this end over here, they will give heat. Okay, they will give heat on this end. And this end, the right side, and they'll keep it cold. Okay. Now, because of this change in temperature, an electricity is produced. Electricity starts flowing. Okay. Have you heard of this anywhere? This is called a thermocouple. Yeah. So whenever you can, where do you find thermocouples? I don't have any example, but not used very often. You don't learn too much about it. You just need to remember thermocouple. Thermo means heat, couple means two, right? So two metals joined with their ends. One end, one terminal, one place where they're joined is heated up, and because of that heat, there is a flow of electricity. So this is an example of heat energy getting converted into electricity.
About toaster,
Was that?
one of the toasters, the bread toast.
Toaster is there's no electricity. No,
Right.
that is electrical to heat energy, just like a oven, like the iron box. Okay, there are resistance wires and they get hot. That's all. Right?
Yes.
Now furnace, we find thermocouple.
Where do you find thermocouple? Come on.
Furnace,
Furnace. For what? Furnace means just to produce heat in the house, no? That furnace you're talking about, or what furnace?
yes.
They're not, I don't know, I have not heard about anything where they're converting that into electrical energy. Anyway, we'll go to the next. Electrical energy to sound energy. Easy one. Where is electrical energy converting to sound? Mic.
Microphone.
Mic is the opposite. Mic is sound getting converted to electrical energy. You're speaking into the mic. So sound is getting converted to electrical.
Speaker.
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 What he said? He's a speaker or what?
Yes. Speakers.
School bell is electricity to magnetism to sound. Yeah. Indirectly. Yeah, same thing. Even these speakers have magnets inside. So electricity is converting to magnetic. There's an electromagnet in the speaker, which creates sound. Okay. So yeah, it's indirectly becoming sound, but yeah, we can say it is a conversion from electrical energy to sound energy. Yeah, and the opposite is sound to electrical. That is the mic. Right, you're speaking into the mic. So your sound energy is getting converted into electrical energy and going through the wire. Right? Are you all getting me? Understand this, okay? You can't memorize it, just understand. Next one, electrical energy into chemical energy. Okay, where is this? It's in a battery. Okay, first you need to see
Battery.
chemical to energy. Sorry, chemical to electrical is a normal battery. A battery has chemical energy stored inside of it. And when you connect the battery to something, that chemical energy converts into electrical energy. Once all the chemicals inside the battery is used up, what happens to the battery? The battery is dead. Okay. Now a rechargeable battery, you are giving inside electricity. So there you see electrical energy getting converted into chemical energy. Okay. So an example of electrical to chemical is what? Rechargeable batteries. Only in rechargeable batteries, the electrical energy converts into chemical. In a normal battery, you only see the chemical energy changing into electrical. Yeah. That's
And
it.
now what about car battery?
Car batteries are also rechargeable. So both ways. Rechargeable batteries, you see both conversions, electrical to chemical and chemical to electrical. So car batteries are rechargeable. All phone batteries are rechargeable. You see both the conversions. When you're using it, chemical gets converted to electrical. And when you're charging it, electrical gets converted into chemical. But in the normal non-rechargeable batteries, there's only one conversion, that is chemical to electrical. Next one, chemical energy to light energy. Okay, where do you see this? Chemical producing light.
Candle.
Yeah, a candle. Okay, there are chemical reactions taking place in the candle. More than the candle, you can talk about the matchstick. When you burn a matchstick, there are chemical reactions taking place there, which gives out light. Anything burning, kerosene lamp. The kerosene is burning. There's a chemical reaction taking place in the kerosene, which gives out light. Have you seen a kerosene lamp? I don't think you would have seen it. When I was small, we had kerosene lamps and all. Why? Because those days there was no LEDs. Nowadays, LEDs, best thing, right? They're so bright and batteries are good. Battery technology also have become better. LEDs also have become better. Put them together, you have emergency lights. Yeah, kerosene lamp, there is a wick. You have to put the fire on the wick, and the wick is dipped inside kerosene. So kerosene continuously is coming to the wick, and it is lighting, and there's light continuously. Okay, so it's like a candle, but it burns for a long time. Next, light energy to chemical. Light to chemical. Where do you see light to chemical? Light becoming chemical. Photosynthesis. Light energy is needed for that reaction, and photosynthesis is a chemical reaction, right? So I think that is the only place where you can see light getting converted into chemical energy. Next, electrical energy to light energy. Oh, very common. Your lights, right? Electrical energy to light energy, your LED bulbs and whatever lights you have. Opposite, light getting converted to electrical. Okay. This is the solar cell. Light energy is converting into electrical energy. There's one type of cell called photoelectric cell. That also same thing. So it's similar to the solar cells. The light energy get converted to electrical. Next, heat energy to mechanical. Heat to mechanical. Heat causing something to rotate or move. So engines. In a steam engine, the heat energy of the steam changes into kinetic energy of the piston. Basically, it is that expansion of water into steam which causes that high pressure that causes the turbines to rotate or the pistons to move around. Okay, so that is heat energy to mechanical. So you can say this in any turbine. In any turbine, conversion of water to steam causes the turbines to rotate. That's an example of heat to mechanical. Then chemical to heat. Chemical to heat. Chemical, some chemical that's burning that gives out heat. Any fuel, kerosene, yeah, petrol. See, there are some more examples here. Explosion of crackers. In Diwali we burst crackers. So there's a chemical reaction that is producing heat. Not only heat, three things it's producing: sound, heat, light. Light. The rockets and all, they give out light here. Okay, so three forms of energy are being produced from that chemical energy. Respiration also, the reaction of respiration, it's a chemical reaction and it gives out heat, right? That's what keeps us warm. So that is also an example of heat to chemical to heat. How many are there? 18.
Does it produce new heat?
What does it produce? What?
Does it produce nuclear energy?
Does what produce nuclear energy?
The fireworks, the crackers.
No, nuclear energy is completely different. That is very high form of energy. It will be a bomb if we have nuclear energy anywhere. Nuclear energy, you need a huge amount of heat to start a nuclear reaction. And the nuclear reaction will produce even much more heat. So if it's not controlled, it's a bomb. If it's controlled, you can use it for producing electricity. So no nuclear in. Then chemical energy to mechanical. So this is in vehicles. In vehicles, you're burning the fuel. So that's a chemical energy. And that burning of the fuel is used to rotate the wheels, create mechanical energy. Then electrical energy to magnetic. This is an electromagnet. In a bell, in a fan, you have electromagnets. So you're giving electricity, which turns into magnetic energy. Then nuclear to electricity. This is what we see in a nuclear reactor. Okay, they are creating the nuclear fission reaction, and that produces electrical energy. Again, how actually nuclear energy is a very high amount of heat energy. That heat energy is used to do what? How does a nuclear change into electrical? The nuclear energy produces heat. How is that heat used? To boil the water. And when the water boils and becomes steam, again rotates the turbines. So it's basically water boiling only. Different methods to boil water. Okay, and the last one is mechanical energy to heat energy. Mechanical to heat. Something moving, creating heat. What is that? Yeah, some frictional energy is produced. For example, when you drop an object, huh? But then that is not mechanical, no, they're stopping the wheel. Mechanical means something that's moving, that's creating heat. As it's moving, okay, he's saying when the tire rubs on the floor, if you're skidding or drifting, then it produces heat. Yeah, that's not a normal example. So here they've given an example of water. When water falls from a certain height on the floor, it hits the floor, hits the ground and produces heat energy. Now we don't notice this because who's checking the difference? But there is a heat which is produced when water strikes on the ground. See, on striking the ground of water, a part of the kinetic energy of the water changes into heat energy, due to which the temperature of the water rises. Also, moving parts, mechanical, like friction. You can give other examples of friction, like a motor or an engine. As it is rotating and moving, it is causing friction, which causes heat. Okay. All right, so the B part is over. You have the C part, which is talking about principle of conservation of energy. This word conservation of energy has been used many times. Conservation of mass, conservation of energy. What is it? Energy can neither be created nor destroyed. It can only be changed from one form to another form. That is principle of conservation of energy. Okay. So in the previous part of the chapter, all this while we saw how energy is being transferred from one form to another. So principle of energy, principle of conservation of energy is being used over here. In the C part of the chapter, you're studying conversion of which energy into which energy. In the C part, we're going to learn potential energy, that is U, changing into kinetic, and kinetic changing into potential. Okay, that's what we're going to learn in the next part of the chapter. Now, yesterday maths gave you some homework, no homework, but you have to study. Yeah, how many of you started studying for the test? You have 3 chapters test. Yeah, if I give an extra day at all, you won't study. That's why there's no point giving. I should just tell you test tomorrow and give you test. Then only you'll study. If I give 3 days, you study the last one day. Okay, you have a test day after tomorrow on Thursday. 3 chapters. Okay, what are the 3 chapters? Linear inequation, reflection, and quadratic equation.
I'm getting problem from linear equation problem.
Okay.
I will send you.
Yeah, send it to me, then I'll tell you what it is. If anyone has any doubt in any of these 3 chapters, please ask me anytime. Send a message and I'll clear it up. Okay. All right, we'll end with this. I'll see you tomorrow. Tomorrow we'll continue with physics, and we'll also do another subject. Which one I told to bring today? I think bio, right? Bring bio and physics tomorrow. Okay. Okay, I'll see you all. Bye. All right, we'll start with the work energy theorem. Okay, work energy. So we already know that work and energy are related. How are they related? Or what statement can you say where you use both these words? You need
Power.
energy to work. No, no, there's nothing to do with power. Power is how fast you do it. How fast you do
Okay.
consume the energy, or how fast you do a work. It depends on time. Work energy doesn't depend on time. It's just that if you have energy, you can do work. There's one more statement having both these words, work and energy. Now, Beryl said, what if you have energy, you can do work. But there is a proper definition where you use both these words. It is the definition for energy. What's the definition for energy? Capacity to do work. So energy is the capacity to do work. You see, that is also a statement where you use both these words. Energy is the capacity to do work, which means if you have energy, only then you can do work. Okay. Let's read the definition according to work energy theorem. The increase in kinetic energy of a moving body is equal to the work done by a force acting in the direction of the moving body. All right, so this is what we're going to derive now. Okay, what this says, the increase in kinetic energy of a moving body is equal to the work done by a force acting in the direction of the moving body. Now let me explain what this means. Imagine there is a car over here. Okay, and that car was already moving at a certain speed. That means it had some kinetic energy. Say it had a kinetic energy of 30 joules. That was the kinetic energy it was moving at. Okay. Now say if Ahmed goes and pushes the car from behind. Okay, so Ahmed is here now, and he is pushing the car. Now, when he pushes the car, say its kinetic energy increased, it became 50 joules. Correct. No, because he's pushing. What happened to the speed of the car? Speed increased, and now its kinetic energy went from 30 to 50. So, how much energy did Ahmed use up?
20 joules.
20 joules. The difference between that change, right? From 30 to 50, it went, right? So, the 20 joules, it increased by 20 joules. That was his energy, which went into the car. This is work energy theorem. So, what does work energy theorem say? The increase in kinetic energy. How much is the increase over here? 20. That increase in kinetic energy of a moving body is equal to what? Work done by Ahmed. Did you understand? The increase in kinetic energy is equal to the work done by a person. Work done by a force. You are applying a force, right? So work done by the force. Is everyone clear of the definition of work energy theorem? So it is a comparison between what? Increase in kinetic energy is equal to what?
Force applied.
The work done by the force. You are the force, you're doing some work. Remember, kinetic energy, it's energy. And work done, that is work. Remember, we said that energy is equal to work. So we're using that here in this. Increase in kinetic energy is equal to the work done by the force. By the force means whoever is applying that force. By whatever. Okay. Now, since you all understood the theorem, right? We'll move on to the derivation now. So here, let a body of mass m be moving with an initial velocity of u. When a constant force F is applied on the body along its direction of motion, it produces an acceleration A, and the velocity of the body changes from u to v in moving a distance s. Okay, so there are so many alphabets used here. You need to know what each of these alphabets are. Okay, so what is u? Which velocity?
Initially.
Initial velocity. That means this car was having an initial velocity of what, Beryl? This was its initial velocity, its initial speed.
30.
No, 30 joules is not velocity. 30 joules is energy, kinetic energy. Okay. But to get that kinetic energy, we had to use, what's the formula for kinetic energy?
Into v square.
mv square. So this v, this v is this initial velocity. Okay, what speed it was initially. Now when you pushed it, its speed increased, right? And it turned into v. V is the final velocity. Okay, so initial velocity is the speed in the beginning, final velocity is the speed later on. All right, then you have F. What is F? F is the force that was applied by Emmett in this example. Force applied. What is M?
Mass.
M is the mass of what? Of the car. Okay, based on the mass of the car, that much force you have to apply. If the car had a greater mass, you would have to apply a greater force. Okay, Neha, it's 5:03. Very late. Traffic. You're joining from home. You should join on time. Okay. All right. So for M is the mass of the car. What is A? Acceleration of whom? No. Acceleration due to gravity is like this for a falling body. This is not acceleration due to gravity. What is the acceleration? The increase in speed. That increase in speed in a certain time is the acceleration. See, when you push the car, what happened? The car accelerated. Its speed increased. So that is this A, acceleration. Okay. Let's do one thing. Let's write these values in the beginning. Okay, force, mass, and acceleration. And here we'll write uv. Okay, what else is there? You have s. What is s? Displacement or distance? So displacement. So in this story over here, what is the displacement? This car moved, no, from here to here. This is displacement. The distance from the initial position of the car to the final position of the car is the displacement. Okay, that is the S. There is one more thing, time. We're not using it here, but if there is time, what would this time be?
From your
From this initial position to the final position, how much time it took for the speed to change from U to V? That is the time. You know, all these values A, U, V, S, and T were used. You learned this in last year. In last year, there was a chapter called Equations of Motion. Do you all remember the equations of motion? There were 3 equations of motion. How many of you remember the 3 equations of motion? I'll give you a hint. The first one started with U is equal to, second one started with S is equal to, third one started with, first one started with V. V is equal to, second one started with S, third one started with V square. Anyone remembers the 3 equations of motion? First one was V is equal to U plus AT. Second one, S is equal to UT plus half AT square. I think I made you tell it like 10 times or something, so you'll remember it. Do you remember? We did this. I don't know if you remember. Okay. And the third one is V square. V square is equal to U square plus 2AS. These are the 3 equations of motion. When do we use these 3 equations of motion? In what type of numericals? When there is an increase in velocity. That means there is an acceleration. What is the meaning of the word acceleration? Huh? Acceleration means increase in velocity. That's the meaning of acceleration, no? If I say I'm sitting in a car, I accelerated. So what happens when you accelerate? When you press the accelerator, what happens to the speed of the car? It increases. So the meaning of the word acceleration is what? Increase in velocity. Okay. All right. So all these 3 equations of motion are used whenever there is an acceleration, or the opposite, whenever there is whenever you brake. What do you call that? Opposite of acceleration is what? What is the opposite of acceleration?
Braking.
Not braking.
Reverse.
No. What reverse? Slowing down. It's called retardation or deceleration. Okay. So the word used in your books are retardation. Retardation means reducing your speed. Okay. I don't have to say this again, but yes, Aman, Ryan, and Sneha, you have to turn on your cameras. Gloria said something you can't turn on, but the rest of you put your cameras on. First of all, Aman, why are you joining online? Aman,
Yes, Anna.
answer.
Anna, I woke up late.
Then put your camera on. You have to be here. If you're joining online, you follow the rules of online. There is 100% sure you won't listen. Okay? You need to be here. Okay, so reminding you of the equations of motions once again. V is equal to, say it out, V is equal to U plus AT. S is equal to UT plus half AT square. And V square is equal to U square plus 2AS. Okay, again, when do we use these 3 formulas? When there is an acceleration or a deceleration. Okay, so whenever there's an acceleration, you have 2 velocities. You have the initial velocity and you have the final velocity. Initial velocity means the initial speed at which the car was in, and final velocity is the final velocity at what the car reaches after there is an increase in speed. Okay. U, V, S, T, and A, correct. So all right, just write down these alphabets and also their units. Tell me, what are their units? What's the unit of force? Newton. Mass, kg. Acceleration, meter per second square. Initial velocity, spelling is wrong. What is initial velocity? Meter. What's the unit of velocity? Speed. Think of the formula. Speed is equal to distance upon time. Meter upon second, meter per second. See, any unit is derived from the formula. Do you know that, everyone? See, if you know the formula for anything, you can tell what the unit is. Okay, final velocity. Meter per second, whether it is a final or initial, it is still velocity. So it's meter per second. Displacement, meter, the distance, no? Displacement is the distance. And time, second. Okay, so these are all the quantities with their units. And these are the three equations of motion. This is a revision of 9th standard, this part. Write this down. First, you write this part down. What's in the box? Okay, continuing, shall we? We're going to use some of these formulas now and derive this relationship between increase in kinetic and work done using these formulas. That's why we need to know them. There's also one more formula using these three, F, M, and A. What was that formula? Using F, M, and A. F is equal to ma. Force is equal to mass into acceleration, right? And also there's a formula for energy, which we saw in the beginning of the chapter. What is energy's formula? Or work done? Work done formula is what? F into S. Okay, so we're going to use those formulas. Okay, so we'll start with, our aim is to do what? Our aim is to find a relationship between work and energy. So we're going to start with the work formula. Write the heading as work energy theorem. All right, so we'll start with work formula. Work formula is F into S. Now, F, we will leave it like that. No. F also we'll put the value. For F, we're going to put the value. What's the value of F? F is equal to ma. And for S also, we have to put some value. Now, is there a formula for S? No, S is a fundamental unit. Fundamental unit means it's not a derived. Remember in 9th standard, we learned fundamental units and derived units. Derived units have formulas. You derive them from the fundamental units. So S is a fundamental unit. It doesn't have a formula. So we have to make a formula for S using one of these three equations of motion. So which one has S over here? Second has, third also has. Okay. Now second has, yes, but second has time. We're not going to use time. So we will use the third formula, which has S. In that there is no time. There is U, there is V, and there is acceleration. Okay, so let's use that. So write that equation, that is V square is equal to U square plus 2AS. Now, if you have to make S the subject, keep this over here, take the U square on that side. So 2AS is equal to V square minus U square, right? If you take the U square on the other side, then take the 2A up on the other side. So that is V square minus U square upon 2A. So this is the equation we got. Okay, so for F, we have F is equal to ma, and for S, we have S is equal to V square minus U square upon 2A. Now substitute these two values in your W formula. Substitute 1 and 2. So W is equal to what now? MA into V square minus U square upon 2A. Okay, can we cut anything here? Okay, the A will get cut off. Anything else? Nothing else. So W is equal to what now? Whole divided by 2. So that whole divided by 2, I'll take it outside, half as half. And then we have M into V square minus U square. Correct, the M gets multiplied into the whole thing, right? So V square minus U square. Now we multiply this whole 1 by 2 M into V square also into U square also. So what we get is W is equal to half M V square. See, something looks familiar. What is half M V square? Yes. Minus half M U square. What was V and what was U? Yes, V was final velocity and U was initial velocity. In other words, this half mv square is what? Final kinetic energy. And this was initial kinetic energy. See, we got our derivation. What is work? Work is equal to the final kinetic energy minus initial kinetic energy. The work done by Ahmed was the final kinetic energy over here. What is the final kinetic energy? 50 joules. And the initial kinetic energy was 30 joules. So 50 minus 30, that is 20 joules. That is the work done by the force who pushed the car. This is the derivation. Did you all understand? Okay, write down the derivation. If you have any doubt, please ask. So thus what we understand from this derivation is that W, which is the work done on the body, is equal to the change or the increase in kinetic energy. Clear? All right. So two theorems we have learned. Last class we learned one theorem. Did you practice that theorem? Anyone? How many are going to get good marks if you practice it? Others, I don't know. Practice. Okay. What was the theorem we did yesterday?
The kinetic energy changes the potential of this.
What is that theorem? It was the relationship. It was the relationship between K and P. That is kinetic energy and momentum. Okay. Both are very similar. Both are dependent on mass and velocity. Okay. But there is a slight difference. Okay. We'll move on to the different forms of energy now. A very simple topic that you can just read. That's why I told you to read and come. So we'll just discuss this quickly. First one is solar energy. So solar energy is the energy that comes from the sun. Now this solar energy has two forms. It has heat and light. Correct? The energy from the sun gives you both heat and light. Now, is it possible for us to use that energy, to convert that energy into some electrical energy that we can use? Yes. How can we convert that energy?
Solar panel.
Yes, solar panels. So what is solar panels? See, actually solar panel is different. Solar cells are different. Okay. So to convert that the solar energy into electricity, we need solar cells. So solar cells are some semiconducting materials so that when light falls on it, it turns into electricity. Okay. That is the most direct form of conversion of energy from light into electrical energy. Okay. All the other forms of electrical energy that we get have to go through many forms to get there. There's so many parts involved. Like if it's hydroelectricity, if the water has to fall on the turbines, the turbine has to rotate, and the turbine has to rotate the generator. When the generator rotates, it converts that mechanical energy into electrical energy. So there are so many steps involved. But solar panels are out. I mean, solar cell, one step. Direct conversion of light to electricity. Is it light to electricity or is it heat to electricity? It's not heat, it's light. Okay, solar cells don't convert the heat, it just needs light, whether it is cold light or hot light. Understand? It's light. So light has to convert. So whether it is winter or summer doesn't matter, because it's not the temperature that matters, it's just that light. Okay, what? Tell no, speak to me, not to Beryl. All right, next, solar panels is just the black color painted metal surface, and this is for heating water. Solar panels are for these water heater. Inside a water heater, I mean, you know the solar water heater, there's a tank and there is a black color. Have you seen it or not?
Yes.
What is inside that black color thing? Huh? See, you've seen this, no? Have you seen this anywhere? If you go on the terrace of any building and then you look, you'll see on top of many terraces, you'll see this thing. Okay, buildings, they set up these things, or if you have houses, they set up these things. This is a solar water heater. What does it do is it heats your water. So you don't need a geyser in the house to heat the water. This will heat the water using the sun's heat energy. Okay. Now you see this thing over here, this black thing here. What do you think this is? Is there a solar cell? It's not solar cells. Okay. This is different. See, it is just, what is it, Nathan?
I called it a solar panel.
Yeah. And what is inside the solar panel? My question is, do you have solars in the solar panel or not? No. Ryan, tell me.
It transfers heat, right? Kind of. I have it on my terrace.
Yeah. So it's there on many buildings. They use this because you don't need electricity. You don't need to waste electricity to heat water. You can just use the sun's, what energy from the sun? Heat, not the light. Okay. Here, this uses the heat energy from the sun. So these are simply black color pipes. Okay. And the water is allowed to pass through these pipes. And when water passes through these pipes, the sun's heat will heat that water as it's passing through the pipes. The pipes are black in color. The inside part of the pipes are black. And what does black do? It absorbs the heat energy, right? So that absorbs the heat and it turns the water hot. And so the hot water is stored inside the tank. That way you don't need a heater. So this is a solar panel that is for heating water. Okay, so that's one use of one use of solar energy. Okay, we're seeing how solar energy can be used. So one was solar panel, one was the solar cells. There's another one, solar furnace. Okay, solar furnace is like a stove to cook food, but using the sun's heat to cook food. So how it is, there is a big concave mirror, and that concave mirror is pointed to the cooker. So when the light falls on this concave mirror, that light will get focused onto the cooker. The cooker will get hot and you can cook food or boil water. See, what they do is they use this to boil water. And when water boils, it expands to form steam, and that expansion can cause the turbines to rotate, and they can even produce electricity using that. Okay, so that is how solar furnace can be used. All right. Next is heat energy. Now, heat energy is a form of energy released when something burns, right? You can form heat energy by burning wood, by burning any fuel, petrol, diesel, coal, CNG, LPG. All of these, when you burn it, it produces heat energy. Now, what do we use the heat energy for? Cooking food, heating water for our daily purposes, daily uses. But also, one main use of heat energy is to boil water to produce electricity. Okay, that is majority of the heat energy produced on Earth is for producing electricity. Okay, so how do they get this heat? Is it using the sun? Is it coal, oil, wood, gas? How do they get this? Surface of? Geothermal. Yeah. Yeah, that is one way to get convert water into steam using the energy from the earth, the heat energy of the earth. That is geothermal. But that is in very few places on the earth you have this geothermal energy. Okay. Why we can't use that in India? Because first of all, the heat in the earth is very deep. To reach that point, you'll have to dig a hole which is like thousands or hundreds of kilometers deep. You can't dig such a deep hole. So geothermal energy can only be used in places where there are volcanoes, where the volcanoes come to the surface. The heat energy from the earth comes to the surface of the earth. In such places, you can put pipes that go into the volcano and come out. Like, you understand? So that heat from the earth will heat that water. But normally, how do we produce electricity on earth is using coal. They burn coal, and the burning of coal heats up water, and boiling of water causes turbines to steam, which causes the turbines to rotate. Um, Heat energy you also get from the sun, right? Sun gives you two forms of energy, that is heat and light. Yeah, so light energy is from the sun. That is a major way we get light energy. But we also produce our own light energy, right? In our homes we have tube lights. That is how we get light energy. In the night, the moon reflects the light of the sun, and that's why you get light in the night. Next is chemical or fuel energy. So this is in fossil fuels. When you burn coal, petroleum, natural gas, we call them chemical energy because there's a chemical reaction taking place, and the byproduct of that chemical reaction is energy, the heat energy. Food also has chemical energy. Okay, there are, huh? Yeah, respiration is a chemical reaction, and for respiration, it uses glucose. Glucose is present in the food, right? So everything that you eat is made up of these chemicals. Okay, and chemical reactions are taking place for respiration, photosynthesis. All of these are chemical reactions. Next, hydro energy. So where do we get hydro energy from? Is windmill is it not hydro? Hydro means water. So hydro energy is tap
Dam.
dam, huh? Okay, so when water
Dam.
is
Dam.
when water is stored in dams, you can allow that water to flow at a very high speed, and that high speed has a high amount of kinetic energy. That energy can be used to rotate the turbines, right? So that is hydro energy. Has anyone seen any dam where they make? I think I asked this question in 8th, right? What there are some dams, only the very big dams, the tall dams, they have very high amount of potential energy. The dams that are short, the water doesn't have so much force, so they can't use that to produce electricity. But dams that are very tall, the water in that dam has a huge amount of potential energy, which can be converted to kinetic energy, which can be used to rotate the turbines to produce huge amount of electricity. Okay, in Kerala there's a Idiki Dam. Okay, Idiki Dam is second tallest dam in India. So they produce a huge amount of electricity. It's very tall. You okay? You're okay? All right. What? Idiki, Idukki, Idiki or Iduki, whatever. All right, the next is electrical energy, one of the most useful forms of energy, right? We use an electrical energy at our homes. We cannot live one day also without electricity. Our phones work on it. We need our phones, no? And light, and we in our homes itself we convert this electrical energy into 10 different forms, so many forms, like fans. So that's electrical to rotational, that's mechanical energy or kinetic energy. And then uh, kettle, in the kettle we're converting electrical to heat energy. Kettle is getting hot, no boiling water. Iron box, yeah, there are so many more examples. We'll be seeing that in the next part of the chapter. Then you have nuclear energy. So nuclear energy is produced when you either break an atom into two or join two atoms into making it one atom. Okay, so joining two atoms is called what? When you join one atom, huh? Nuclear fusion. Okay, suppose you join hydrogen plus hydrogen, what do you get? H plus H H plus H is not H2. H plus H is He. This is a nuclear reaction. What you all are telling me, H plus H as H2, this is what reaction is this? H plus H is H2. This is a chemical reaction. Okay. And H plus H gives helium is what type of a reaction?
Nuclear.
Yeah, it's a nuclear reaction. Okay. In a chemical reaction, two atoms are joining. What is joining about in those two atoms? The electrons. The electrons are taking part in the sharing. The nucleus is there only. Nothing is happening to the nucleus. Only the electrons in the outermost orbit are taking part in the reaction. Right. But in a nuclear reaction, what happens? When two atoms come together, what happens? They both join and become one bigger atom. That is a nuclear reaction. Okay. So two types of nuclear reactions are there. Joining of two is called nuclear fusion. Okay, physics chapter 2, C part, conservation of energy. So conservation of energy means energy cannot be created nor destroyed. You can only change energy from one form to another form. Right. We see energy changes taking place every time. In the last section in B part, we saw how energy is changing from one form to the other form. Right. We saw electrical energy changing into heat or into light, or light changing into electrical or chemical, or mechanical changing into electrical. So many forms of energy we saw changing. Right. So when this energy change takes place, what happens is all the energy from one form changes into another form. Okay. Sometimes some of the energy can get lost into some useless form. That also happens, but it's not destroyed. Okay. Now, for example, if you take a ball and you're dropping the ball from the top, the ball is having energy. What energy does it have? That's kinetic energy. In fact, its kinetic energy is increasing. How is it increasing? From where is it getting more kinetic energy? Is it creating kinetic energy as the ball is falling down from the sky?
Potential turns into kinetic.
Yes, the body had potential energy that is getting converted into kinetic energy. Okay. And as the ball hits on the floor, where is all that energy going? Is it disappearing or is it getting converted into some form?
Heat.
Okay, it's getting converted into what all forms? When you drop something on the floor, you can hear a sound, right? So part of it is getting converted into sound. Part of it is getting converted into heat energy. When it falls, that impact will cause some amount of heat. Okay. Sometimes it might cause some what sparks, which could be a light energy, frictional energy. Okay, so there are different forms of energy that are being formed, and this energy is just getting dissipated. Dissipated means it is just getting spread into the earth and into the air, and it looks like as if it disappeared, but it's not disappearing, it is getting dissipated. What is the meaning of dissipated? Spreading in such a way that it looks like it's disappearing. Okay, it is just going into the air and to the earth. You know, the earth can just absorb how much ever energy you give it, and it will just eat it up. It'll look like as if the energy just disappeared. Okay, but what does it do actually? It is absorbing it and spreading it out into the earth because the earth is very big. For example, a lightning. You know, lightning has so much energy. When a lightning falls onto the earth, where is all that energy going? It's just spreading throughout the earth. It's getting dissipated.
Yes.
Okay. If somebody's standing even few meters away, they won't get the shock because the earth just absorbed all that energy and just spread it into the earth. It is not staying in one place. Okay. All right. So in this part of the chapter, we are seeing how energy change is taking place from one form to the other. We are studying about kinetic to potential. Okay. For a ball that is being dropped from a point A to a point C. Okay. So initially the ball is at point A, it's falling, it comes to a point B, and then finally it lands on the ground, which is point C. At all these 3 points, the body has mechanical energy. Mechanical energy is divided into two. That is kinetic energy and potential energy. Right. So we're going to calculate what is the kinetic and potential energy at all these 3 points. Okay. Starting with the top. Now at the top, what is the kinetic energy? What is the potential energy? Okay. Now, kinetic energy is 0 because the object is not moving. It is at rest. Right? Since the object is at rest, it is not moving and there is no kinetic energy. So 0 kinetic energy. What is the potential energy? So potential energy has a formula. What's the formula for potential energy? Tell me the formula for potential energy. Come on, everyone.
MGH.
mgh. Okay, so m is the mass of the ball, g is acceleration due to gravity, and h is the height at which the ball is. See, this is h. Okay, the height from the floor till that where the ball is, that is h. Okay, so the total energy, if we add these two, what is the total energy that the ball possesses at the point A? I'll write T for total energy. That is 0 plus mgh. So that is mgh. Okay, the total energy at point A is mgh. Is that clear, everyone? Now we're going to do the same thing at point B. We're going to find out what is the kinetic energy and what is the potential energy. Okay. Now, when the ball comes to point B, this distance, that is from A to B, we'll call that distance as x. Okay. And the distance from B to C, what should we call that as? Don't create more variables.
2x.
No, we don't know if it's double or triple or whatever. But it's the remaining height. See, if the total is h and A to B is x, then what is B to C?
X plus Y.
There's no y. We only have two variables, h and x. H is the total, x is AB. So BC will be what?
H minus X.
H minus x. H is the total, and minus x, you will get the remaining, right? For example, if my height is 5 meters, okay, and my body is 4 meters below my neck. So my head is how many meters?
1. After minus, you will get 1.
5 minus 4, right? That's how we get the BC, H minus x, okay? Okay. So at position A, we have found out what is the total energy, that is mgh. Now we'll check at position B. So at B, we have to find out what is the kinetic energy and what is the potential energy. Okay. So kinetic energy formula. What's the formula for kinetic energy, everyone?
Half into m into v square.
Okay, half mv square. So m is the mass of that object or the ball, and v is the velocity at point B. Correct? V is the velocity of the ball at point B. Now, what is the velocity at point B? So we need to find that out. So we need to use one of the equations of motion. Last year you had 3 equations of motion, which I revised with you, I think, in the beginning. So what is that equation of motion which had V in it? Remember, V square is equal to U square plus
Use 2as.
2as. Yeah, this is the formula that we have for V square. Okay, now what is our aim is to find the velocity at point B. Okay, so what is U, what is A, and what is S? What is U?
Initial velocity.
U is the initial velocity. So what was the initial velocity of the ball when it started? How much was it? The ball started from rest, no? So the initial velocity is 0. Okay. What is A? What is the acceleration of the ball right now? Gravity is pulling it down, so there is acceleration due to gravity. How do we represent acceleration due to gravity? We use the alphabet G, correct? G is the alphabet for acceleration due to gravity. And what is S? S is the distance it covered, okay, from the time it was at rest. So what is the distance it covered from the time the ball was at rest? That means from A to B. What's the distance from A till B? X. From A to B distance is X, right? Okay. So we substitute these values in place of V in for V square. So V square is equal to U square, that is 0 square plus 2 into A. A is G and S is X. So V square is equal to 2GX. Do you understand this? Is everyone clear with this part? Have we got this? Okay, now in the same kinetic energy formula, we will substitute this value for V square. So kinetic energy is equal to half into M into V square. But instead of V square, we will write 2GX. Is everyone clear how we got this? So we cut this 2 and the 2. And what do we get for kinetic energy? mgx. Do you all understand how we got mgx? M into G into X. This is a very important derivation, okay? If you don't understand, please ask. We're going to finish this derivation today. So listen carefully and understand it. So what we have figured out now is at point B, the kinetic energy is mgx. Okay? I'll just call that equation 1. Now, let's find out what is potential energy. So formula for potential energy is mgh. Okay? So m is the mass of the ball, g is the acceleration due to gravity, h is the remaining height. From the point B, how much remaining height is there before it reaches the earth, before it reaches the ground? The remaining height from B to C is h minus x. Right? Okay, so that is U. U is equal to mgh minus x. We'll call that equation 2. So we got K and we got U for the point B. Is everyone clear about this? Now let's add both. Let's find the total mechanical energy. The total mechanical energy is K plus U. So K is mgx and U is mgh minus x. Correct? So if we simplify this, we'll get mgx plus, this will be mgh minus mgx. Correct? If we multiply mg into h and mg into x, this is what we're going to get. So now from here, mgx will get cut off because one is plus, one is minus. And so we have the total energy here as mg. Did you notice something? The total energy at point A was how much? That was also mgh. And the total energy at B is also mgh. Is everyone clear about this? Okay, I want you to write this much down. The A and B. Okay, then we will do C after this. Okay, till now what we have seen is total energy at A is mgh and the total energy at B is also mgh. Write down this and then we will see the total energy at C. Okay, so what we have seen till now is at point A, the total energy is mgh. At point B also the total energy is mgh. Okay, now let's look at the total energy at point C. That also should be mgh, right? Because that's what we're trying to prove. We're trying to show that at any point, the total energy will be a constant value. In this case, it is mgh at all the 3 points. Okay. So now at point C, let's see what is kinetic energy and what is the potential energy. So for kinetic energy, we'll use the same formula, which is half mv square. Okay, we still need to derive what is v square. So v square formula, we have the same formula, which is u square plus 2as. So at this point, what is u again? U is 0, because at the starting it was 0. What is A? A is acceleration due to gravity, that is g. And s is the distance it covered. So the distance it covered will be h. Okay. So v square, if you substitute these values, v square is equal to 0 plus 2gh. In other words, v square is 2gh. Substitute this value in place of v square. So kinetic energy will be half into m into v square which is 2gh. So here we cut the 2's and we get the kinetic energy as mgh. Okay, we'll call that equation 1. Next, potential energy. What is the potential energy at point C? Remember, C is at the ground level now. So at the ground level, what is potential energy? At the ground level, there is no potential energy. It is 0. Correct. So now if we find the total energy means kinetic plus potential. We are getting what? mgh plus 0, which is mgh. Okay, so we have proved our theorem here. So what is the theorem status? At all the 3 points A, B, and C, the total energy will remain same. That's what we have proved over here. The total energy at all the 3 positions is mgh. Write this down. Yeah. So again, I'm saying you have an object at a certain height. Now we know everything about the height. We know the height of that object. Okay. Now the object is dropped to the ground. When it is dropped to the ground, all that potential energy which it had gets converted into kinetic energy. And their question is find the kinetic energy possessed by that body. Now to find kinetic energy, what do we normally need is m into v, mass and velocity, half mv square. We know the mass, but they have not given velocity. So we cannot use the kinetic energy formula to find.
So first we can use. So first we can find the velocity by velocity formula.
No, but to find velocity, you need certain things. That is also not given. What they'll give is they'll give you mass and they'll give you the height. This is what is given, mass and the height of the object. So using this, how can we find the kinetic energy? So we don't find kinetic energy. We find potential energy, which is mgh. Mass is given, height is given, g we know. So we can find potential energy. And now what we know is all the potential energy got converted into kinetic energy. Right? So whatever potential energy the object had at the top, that is the kinetic energy when it comes to the bottom. Do you understand? So you're not directly finding kinetic energy. You're finding potential energy and then you're writing a statement that all the potential has been converted into kinetic energy. Therefore, kinetic energy is whatever potential energy is. Ahmed, what is that sounds? I can't understand. Okay, did you all understand this type of questions in this exercise? Okay, so let us look at a question. Look at this third question here. A metal ball of mass 2 kg is allowed to fall freely from rest from a height of 5 meters above the ground. Take g as 10 meter per second square. So what all values were given? Huh? See the mass 2 kg, the height h. Just as I said, no, m and mass and height will be given, and g also. Height is 5 meters and g is 10 meter per second square. So they've given m, g, and h. First question is calculate the potential energy possessed by the ball when it is initially at rest. Okay, so what is the potential energy on the top? U is equal to mgh. That is 2 into 10 into 5. So 2 5s are 10. 10 into 10 is 100 what? Energy. What's the unit of energy? Joules. Just think of what you're finding. You're finding energy. So 100 joules was the energy when the ball was, or whatever, yeah, metal ball is at that certain height. Is that much clear? Now look at the second question. Calculate the kinetic energy of the ball just before it hits the ground. So kinetic energy, what is the kinetic energy? We cannot find it using this formula. Why? We don't have velocity. So we write that statement that I said. What is that? Kinetic energy just before hitting the ground is how much? What is it? Is equal to
100. Potential energy.
the potential energy when it was at the top. So how much is that? 100 joules. Do you all understand or not?
Yeah.
So it had 100 joules on the top, and when it just before hitting the ground, all the 100 joules, which was potential energy, got converted into kinetic energy. Okay, that's the answer. Last question. What happens to the mechanical energy? What is mechanical energy now? What's mechanical energy? Someone, at least one person. We finished this chapter. What is the meaning of mechanical energy? Potential and kinetic together.
Potential kinetic.
Yeah, so the potential energy got converted to kinetic. So everything was that mechanical energy only in two different forms. It just changed from one form to the other form, and both were mechanical. Now the question is, what happens to the mechanical energy, which means that that kinetic and potential together, after the ball hits the ground and comes to rest? It hits the ground, comes to rest. Where did all the energy go? What happened to it? Did it get destroyed? Did the energy just become zero? Energy cannot become zero. But that ball is at rest, which means it has no energy. So what happened to the energy? It got converted into what? When something falls down, you hear sound. So sound energy was created. Sometimes heat energy when it hits
Friction.
some friction, some heat. Okay, so all different forms of energy it was converted into. And all this energy, sound just went out, dissipated into the air. Dissipated means just got spread out in such vast amount that it became zero. Some of the energy went into the earth and there it got dissipated. So the energy just spread out into the air and into the earth and got dissipated. You can't say disappeared, dissipated. So the answer here, mechanical energy converts into heat and sound energy. Just that much is enough. Okay, but you understood what's happening? It's getting dissipated. So write that statement, complete this. If there's no forward,
If there is no gravity in space, I have seen on video one guy is jumping from space but from there is
because that is this gravity. The gravity of Earth, it's not like when you go to space, there's no gravity. In space, there is no air, but there is gravity. How is the Earth staying in its orbit? Gravity of Earth and gravity of Sun are holding it together. So the gravity of the Earth is felt much farther than space. Okay, but it gets lesser and lesser.
Is gravity, so why do not we come down?
What?
In space there is gravity, so why how the gravity takes pulls, so why like that we do not come down?
If we are quite close to the Earth, say outside the atmosphere is only 300 kilometers. but gravity extends thousands of kilometers above the Earth. So if a person is 1,000 kilometers above the Earth, he's outside the atmosphere, but he's still inside the Earth's gravity. He will still fall into the Earth. Okay? Unless you go very
Yes.
far away from the Earth, then there's no gravity of the Earth felt. Okay?
Yes. Done, sir.
Okay, let's see this next question. The diagram given below shows a ski jump. You know, it's a ski jump. They're skiing, they have that long blades they're on, and they go down the snow mountain. Okay.
Yes,
All right.
sir.
A skier weighing 60 kgf stands at A at the top of ski jump. He moves from A and takes off for his jump at B. So he goes down and then he takes off. He's flying over here. Understood? Okay. Calculate the change in the gravitational potential energy of the skier between A and B. So between A and B, what was the change in its gravitational potential energy? Which means find its potential energy at A, find the potential energy at B, and then find the change. Change means what? A minus B, the difference. Okay. So what is its potential energy at A? MGH, M is how much? 60. G is how much? 10. H is how much? 75. So we can find his potential energy at A. Same way you can find his potential energy at B. The height only is changing over there. Right. And then minus both, you'll get his change. Do that much? Okay, did you get the answer? How much? Which one? A or B or and B? The subtraction. Okay. So if you do U of A minus U of B, how much you getting? 36,000 joules. Right. So
Yes.
they have written the answer as 3.6 into, this is standard form. The standard form means you are moving the point till here. So you're moving it 4 places back. So into 10 raised to 4 joules. Okay, that's how the answer is in your book. Now, second part of the question. If 75% of the energy in part A, this one, becomes kinetic energy at B, calculate the speed when the skier arrives at B. Okay, so this was the, what is this? Okay, so what answer we got here? This was the change in potential energy. Right, the potential energy decreased by this much. How much was UA? Tell me. 45,000. And U at B? Huh? 9,000. So this energy is what now actually is the kinetic energy. See, initially there was 45,000 joules of potential energy. And at B, there's only 9,000 joules of potential energy. So where is that remaining energy, this much? What happened to that? This is that got converted into kinetic energy. Okay, so basically this is supposed to be the kinetic energy of that skier at B. But what they're saying here is only 75% of this energy got converted into kinetic energy, not the whole thing. The remaining 25% of energy was maybe friction or wind energy. Yeah, friction mostly, because as he's skiing, there's a lot of wind. So he lost a lot of energy through wind friction or even skiing friction. Okay. So what is 75% of this energy we have to find out? 75% of 36,000. So that will be his kinetic energy at B. Okay. So kinetic energy at B will be 75% of 36,000. Then we have to find out what is his velocity, small v. For that, we will use the kinetic energy formula. Kinetic energy is equal to half mv square. We got the kinetic energy from here. We have his mass. We have to find his velocity. Is that clear? Do that, everyone.